All right, section 2.2, we're taking a look at sets, and we haven't yet talked about what sets are. So the first thing that we need to do is we need to look at a little bit of vocabulary for what is a set. So a set is simply a collection of objects. So you can talk about a set of books on your bookshelf, a set of CDs. Do you guys still even know what CDs are? Oh, that's good. A set of CDs. Set of DVDs. You can also talk about a set of people, and that's okay. So it can be human objects, if you will, as well. Okay, so a set of your cousins, a set of your siblings, a set of your family members, things like that. The elements are the individual objects in the set. So that's, if you're talking about the set of books on your bookshelf, your math book would be one of them. Hang on. Let me make it straight up and down. A little bit more square. All right. So if you're talking about a set of objects, that the objects themselves are called elements, and the elements are the individual books or the individual CDs or the individual cousins, whatever those are. Okay. There are two ways to describe sets. One is called the listing or the roster method, and the second one is set builder notation. Now the listing and the roster method works really well when you have a small set, because what it really is writing everything down inside of curly braces. So you write numbers down. So like let's say we're describing the numbers that are from 1 to 5. I'll move in just a second. So this would be 1, 2, 3, 4, and 5. And you write it inside of curly braces. That's the listing or the roster method. We'll use the same method, and it's not going to look like it's very helpful because the set's so small. It's going to look like a lot of unnecessary language. But the second piece is called set builder notation. And for this particular set, you start with you always start with curly braces. And you always start with a variable, so we're going to use x and a vertical bar. So we read this as x such that. That vertical bar is the word or phrase such that. Okay, so this is x such that. The first thing I want to do is I want to say that x, and I'll tell you what this symbol is in a minute, just it's a curly E looking thing. X is an element of the natural numbers. It doesn't matter whether you write them first or second. This is an N. It's got 2 lines on the left. When it's in print form, it usually just looks like a very bold line on the left. So it doesn't always look like double lines on the left. This says N is a natural number. We'll talk about the natural numbers versus other types of numbers in a minute. But this is still telling you N is a natural number. And then you put a comma, and you also say that the N value is less than or equal to 5. So it's a natural number, and it's less than or equal to 5. This E is read is an element of. Okay, so it's in the collection. It belongs to. So this is like saying, I'll use mine, for example. So this is all x, such that x is an element of the hands family, and x is a female. That would be a description and a notation like this. Okay? So that would include myself and my 2 daughters. If we were describing our collection, we could write down my name, Krista, Abigail, and Lilise, and we could put them in curly braces. This works really well for numbers, and it especially works well if the numbers are including a lot of numbers. Like let's say this is all the numbers less than 100. I don't want to write them all out, right? This is a shorter way of writing it. Okay, so let's talk about some of the different symbols that are used that I just described. The first symbol was that E thing, and it is curly, okay? It's not a capital E with brackety looking bold. It's not the capital E. It is a curly E, okay? This is read is an element of. Is an element of. And then there's several more symbols. I used one of them. What was the other symbol that I used on the last slide? Yeah, the natural numbers. So 2 lines on the left, and it looks like an N otherwise. These are the natural numbers. So what are the natural numbers? Well, the natural numbers, and they're sometimes called the counting numbers, are the first numbers that a child learns when they're learning their number system. What do they start with?
1.
1. Start with 1. That's important. And what do they include? 2 and 3 and 4. They're the numbers you learn when you learn to count. So these are what are called the natural numbers, or the counting numbers. So somewhere in, it's probably kindergarten now, kids start learning to subtract. Not kindergarten, you're at least in first grade, right? And as they're subtracting, one of their subtraction facts looks something like 3 minus 3, and you get the number 0, and that's not in this list, is it? Of course, it's a number. We should have a name for it. What kind of a number is it? And so the kind of numbers that include this are whole numbers. That's a terrible W. So 2 lines on the left, and then there's a W. These are the whole numbers, and they're just like the natural numbers, except that they include 0. Okay, so very little difference than the natural numbers. Same as the natural numbers, but they include 0. And then it's about 5th grade-ish, maybe 6th grade, depending on your curriculum. Somebody says, okay, but what if you do 3 minus 6? Get negatives. And you're like, no, I don't do 3 minus 6. Don't do that. Right? So you get negative numbers. And those actually, let me see, your book does them differently. Well, okay. Usually they're used the letter Z for these. I believe your book actually uses the letter I, and it is like a double I, so it almost looks like a 2 or a capital, like a bold line in between. These are actually called the integers, and I'm not 100% sure, but I think the Z actually comes from Latin somehow, just so you know. These include all the numbers that you've had so far and their negatives, okay? So you have, I'll put my 3 dots, -3, -1, 0, 1, 2, 3. They're the integers. I'd rather you use Z. I is not so good because I actually has other meanings as well. I could be used to mean imaginary or irrational. Unfortunately, we have lots of I's for our number systems. So it's not the best choice of a letter to use. Z is more commonly used. Okay, so it's also in about 5th grade that you start dividing things, maybe even 4th grade these days. You actually legitimately start dividing things that don't divide evenly, right? Instead of doing 6 divided by 3 and 6 divided by 2, you do 6 divided by 5. And it doesn't end up to be a whole number, right? What kinds of numbers are those? There's several words for them. It's not irrational, it's rational. That's the all-encompassing word. You get numbers that look like what? Decimals or fractions. Those are typically what you're dealing with. So they're called rational numbers. The letter they use is Q. Any idea why Q would be used for rational? It's because of the word quotient. Quotient is division, right? So a quotient is 2 number that's divided, and rational numbers have that form. At least it's one of the forms they have. So these are rational numbers. And the issue is that they can be written as a fraction. So can decimals be written as a fraction? Yes. Can whole numbers be written as a fraction? Yes. So whole numbers are also rational. The number 3 would be a rational number. Okay? But so would the number 2.7. And so would the number 6 over 3, 6 over 4, 6 over anything that you can write as a fraction. Okay? All those would be rational numbers. And then the other one that we're going to see used is an R. And these are real numbers. And if we're sort of expanding our universe of what numbers we're including, the things that didn't get included that we didn't include before are things like what?
Imaginary.
We don't include imaginary. Those are actually a different category we're not going to use. But you're right. We haven't included them. What else?
We don't include your decimal
Repeating decimals can be written as fractions. Like think about 0.3 repeating, it's 1 over 3. Something else. Pi. Pi is a good example. Pi would now be included. There's one other type of number you haven't thought of, or at least you haven't said. What'd you say, Beth?
I said exponents.
Not exponents. Those are already included. How about square root of 2? Right? If you put that in your calculator, it gives you some funny decimal expansion that doesn't repeat or look like anything specific. Yeah. So this includes everything before. So all above plus, and we'll say values like pi. Another one you may have seen before is e square root of 2. So that's not an all-encompassing list by any stretch of the imagination. But it's a few of the items that we didn't include before, and they do get included in the category ration, or real numbers. Okay, category real numbers. The ones that you will see used the most are natural numbers and whole numbers and integers. Those three at the top. Okay, those are our three you'll see the most used. And of course the element symbol, that will be used all the time. Okay, so the first thing we're going to take a look at is an example. Example number 1, we're going to write the set of natural numbers less than 5 using the listing or roster method. Those are the same method. So what would that look like if we wanted the listing or roster method with the numbers that are less than 5? Okay, so natural numbers, we would start with a curly brace, so don't forget your curly brace. And then what would we start with? 1, because it said natural numbers, like not whole numbers, right? And where would we stop? 4. Because it said less than 5, as opposed to less than or equal to 5, or less than 6. Set builder notation starts with a curly brace as well, and an X and a vertical bar. Always starts that way. And then it includes 2 facts. It's got to include the category of numbers you're pulling from, and it's got to include any other details that limit what the numbers can be. So the category here is natural numbers. And again, it doesn't really matter which order you put these in. I'll put the natural numbers order first, but if you put it second, that's totally fine. And then what other category of numbers or what other description is it giving you about this particular number set? It's less than 5. So we need X less than 5. So those would be 2 ways of writing the same set of numbers. So just be aware, careful that you know the difference between the two, because it will ask you potentially for one or the other, and if you give the wrong one, then you're not following the instructions in the particular problem. Does that make sense? Okay. All right, let's talk about types of sets. The first one is equal sets. Equal sets are 2 sets that contain exactly the same elements. Exactly the same. So verbally, if I described my family, immediate family living in my house, and my husband described his family, immediate family living in his house, those would be equal sets, because those are exactly the same elements that we're talking about. A one-to-one correspondence is a pairing of elements between 2 sets, such that each element in one set is paired with exactly one element of another set. Okay, so if there's 6 elements in one set, there would be a one-to-one correspondence between the elements in my family, because we have 6 people that are living in my house that are my family. Does that make sense? Okay, so we could pair them up 1-to-1. So we go out with another family has 6 people in it, we have 6 people in it, we each have a partner, right? We each have somebody to ride rides with at Six Flags. It's a one-to-one correspondence. Now, if we have that one-to-one correspondence, we call those sets equivalent. So equivalent sets are 2 sets for which there exists a one-to-one correspondence between the sets, i.e., they have the same number in them. 6 people in my family. Who has 6 people in their family? Yeah. at least, no, I need exactly, Catherine. You got so many more than that, don't you? Rayleigh and Rayleigh. You got Rayleigh and Rayleigh. Man, fantastic. I'm going to use both you guys. So Rayleigh and Rayleigh's families, they go out together, and everybody has a partner to talk to, and nobody has to feel left out, right? It's fantastic, okay? Those would be equivalent sets. They're not equal, agreed? Because they don't include the exact same people, but they are equivalent. So you're going to just have to get over the idea that for the moment, equal and equivalent do not mean the same thing. Good with that? All right, an example. Whoa, that was really small. How many ways could we then pair? Do I have 6 here? I do, 6. Oh. How many ways could I pair up Rayleigh and Rayleigh's families so that everybody has a partner to ride the ride with? That's the question, okay? Now, I didn't show you how to do that before, but I'm going to show you how to do it now. So let's take, for example, Rayleigh Farquhar. Was that saying it right? Rayleigh Farquhar. We're taking Rayleigh herself. Okay, so Rayleigh walks into the other Rayleigh's family, and she says, I want to ride a ride with somebody. We're all going to Six Flags together. Who's my riding partner? How many different choices will Rayleigh have of the person who's going to ride a ride with her? 6, because there are 6 people in the other family, correct? Rayleigh has 6 choices. So, whoops, let me get a line here. I'm going to write this down. Rayleigh walks in, she has 6 choices. Once she has her riding partner and their buddy-buddy, and they go off to ride their ride together, and Rayleigh's mom, one of these 6 people, fantastic. Rayleigh's mom walks in. How many choices does Rayleigh's mom have on who she rides her ride with? 5, because there are only 5 people left in the other Rayleigh's family for her to choose from, right? Yeah. So second person, 5 choices. How about the third person? 4 choices. And then after that we would have? And somebody doesn't get a choice, right? It's at the end, somebody is stuck with somebody else, right? Here's what we do. We actually multiply these together. And this will be the number of ways that these pairings could have taken place. So what is 6 times 5 times 4 times 3 times 2 times 1? Grab a calculator. This might be the first time this semester we've used it, right? It might be. Almost, anyway. 6 times 5 times 4 times 3 times 2 times 1. 720. There are 720 different combinations. Correspondences is how this one phrased it. Let me use the word that they're using. Correspondences. So is it any wonder when we get to Six Flags we have trouble figuring out who we're riding a ride with? Man, all those choices. That's if I have 6 people and you have 6 people. What if we have more? All right, so this is how you would do this. Now, what if there were some conditions? Let's say, for instance, that they went and Rayleigh already knew at the beginning they were riding rides together, right? Then when Rayleigh walked in the room, Rayleigh wouldn't have a choice. She'd already made her choice, and there was one choice, right? So the first place that we would have written down would have actually had only one choice. Does that make sense? And the second person only has 5 choices, and so on down the line. So it would change the order of or change the options for what was going on. What if there was a condition and it said something like, only, oops, I didn't mean to do that, only boys ride with boys and only girls ride with girls. Would that change how many choices everybody has? Well, yes, it would change how many choices everybody has. So you're going to have some examples where they're going to limit the number of choices of things you're going to pick, and you have to pay attention to that limiting to figure out how many choices people really have, or letters or numbers or whatever their conditions are that they're giving you. Okay? All right. A couple words to decide or to define for you. Cardinal number. A cardinal number is the number of elements in set S. It is written lowercase n. This isn't on there. Of the capital S. So it almost looks like function notation, f of x, right? The n at the beginning, those parentheses, and then the capital letter S. And those parentheses don't mean multiplication. N and S are not separate variables. It's just a way of describing something without writing out the number of elements in S, because that's long. Okay? So you see N, you see capital S, and it means the number of items in S. So if we were looking at my family or Rayleigh's family, N of S would be 6, right? 6 elements, 6 people in the family. A finite set is a set for which the cardinal number is a whole number. So everyone in this room, if we talked about your families, you would have an N of, put your name in the blank, families, number. You would have a number, and it would be finite because it's a whole number. Right? It's not a fraction. It's not a decimal. You don't have half of a person in your house. Promise. The dog does not count. Does not count. Not in any way, shape, or form. So N of S would be a whole number. That's a finite set. Now, its counterpart is really not fractions, although I joked about that. The counterpart is something that's called an infinite set. An infinite set is a cardinal number which is not a whole number. And we don't mean not a whole number like a fraction. We need not a whole number like, you know, when God tells Abraham to count the stars in the sky and he says, I can't do that. He count the sands in the seas. It's infinite, right? It's not possible to count. Okay, there's no number I can associate with that. In fact, my son asked me this morning if, he didn't use these words, but this is what he's trying to get at. If the number of blades of grass in our backyard was more than the number of people in the world. That's what he asked me. What a weird question, right? Profound. And I told him, I don't think so. I think there's more people than the blades of grass in my backyard. I think that's probably true. But I don't want to go counting to try and figure it out either. All right, so that's infinite set. The last one here is a null set. A null set is a set that contains no elements. It's a cardinality of 0, and there are 2 ways that you can write it. One option is that you write it as a 0 with a slash through it like this. So now, some of you might actually write your zeros that way. You can't do that. It means something different. Actually, I have a couple of meanings, but for what we're using in this class and this material, it means the empty or the null set. The other notation looks like a curly brace with nothing inside of it. Curly brace with nothing inside of it. So we can make a description. It's just a description that has nothing in it. So I can tell you how absolutely phenomenal the babies are that live in my house. They're wonderful. They never cry. I mean, they change their own diapers even, right? They wake themselves up in the morning. They get their clothes on. The babies in my house are fantastic. Because in my house, there are no babies. I'm talking about something that doesn't exist. It's a null set. It's a description. I can talk about it, but there's nothing in that set. The cardinality of that set is 0. Okay? So let's look at some where we're actually figuring out what the cardinality of the sets are. Our question here is to simply figure out what is the cardinality of each set. And just so that we have some notation to describe it, we're going to change these to capital letters and pretend like they are the names of the set. So we have set A, set B, set C, and set D. And we're going to talk about the number of items in each set. So we have little n of capital A. The number of items in set A. So the numbers start at 9 and they go up to 99. And you've seen and counted some of these things back in section 1.2 with patterns and Gauss, right? Remember him? Yeah? So this isn't the first time we've encountered this. How many items are there from 9 to 99? 91. Okay, so how did you get 91, Catherine? I heard yours first.
Subtracted 8 from 99 because that's all that's missing from this set is numbers 1 through 8.
Okay, so we subtracted the number before, the numbers that are missing at the beginning of this set, which is the numbers 1 through 8. That's 8 of them. 99 minus 8 would give me 91. So n of A is 91. How about n of B? The numbers from 2 to 2002, and it skips. It's just the evens. Okay, that wasn't what I meant to do.
1001.
I should just stop messing with this thing, shouldn't I? Yes, Dr. Hands, please quit it. Okay, what did you get, Catherine?
1001.
Okay, does everybody agree with 1001? Disagree? How do you get 1001? Rebecca, you shake your head. Do you know how she got 1001?
Yeah, she divided it by 2.
Right. So we have 2002 here. And why do we divide by 2?
Because we only have to.
Yeah, we have only the evens. We have every other number, half of them, right? So 2002 divided by 2 would be 1001. All right. They're going to try and trick you on C and D. Just need to figure out what they're actually talking about. Okay, so let's see. We have this set builder notation. The first one says x squared such that x is equal to 1, 3, 5, all the way to 99. So let's first just write down, if we were writing in listing method, what is the set? Well, it's the set of these numbers squared. Okay, so the first one is 1, or 1 squared. The second one would be 9, which is 3 squared. And then we'd have 5 squared. I'm going to keep using the numbers themselves without writing them down, just because it's going to be easier to see the pattern here in a sec. And we have 7 squared, and we have it all the way up to 99 squared. So let me ask you the question of the day. Does the square matter? Not at all. It doesn't make any difference on this one, does it? I have all the same number of numbers. I'm just squaring them. So the numbers themselves are different, but how many of them there are is the same. How many of them there are is simply the numbers from 1 to 99. So looking back at the numbers 1 to 99, I can answer the question without the squaring. How many numbers are there from 1 to 99?
45.
Nope, but you're close.
46.
Nope. What'd you think?
49.5.
But can there be half of a number, Sabrina?
No.
No, but you're really close.
50.
There's not 49, there's 50. So let's talk about where 50 is. If I asked you for the numbers from 2 to 100, we wouldn't have a problem, because we would have done what Sabrina said. We would have taken 100 divided by 2 and we got 50, right? It's the even ones. But if I go from 2 to 100, I consider evens, and I go from 1 to 99, I consider odds. It's the same thing. These are the numbers from 1 to 100. It's just the odd ones. We talked, when we saw this kind of an expression before, back with Gauss's method, that one way to do this would be to take 99 and subtract the one that comes before the listing of numbers. In this pattern, what comes before 1? Negative 1. In the pattern, it's negative 1, because these are only odds, right? So if I took 99 minus negative 1, I would actually get 100. That's one way to think about it as well. Any which way you think about it, there are 50 numbers. This is small enough that if you really, really had to, you could count them up, right? It's only 50. It's not 500, right? There are 50 numbers. All right, last one, and we'll stop for today, part D. All x such that x is equal to x plus 1. Says x is a natural number. Okay, so pick me a natural number, any natural number. Don't make it big because there's no need. 3. Okay. This would say 3 equals 3 plus 1. What's 3 plus 1? 4. Does that work? No, 3 doesn't equal 4. So 3 is not an example of a number that works in this set. Somebody go out on a limb. What's going on here? Yeah, there's nothing here that works, right? There is no number that when you add 1 to it, you get the same number. It doesn't work. So this would actually be the empty set. So this is n of d. It equals 0, because this says the number of items. The number of items is 0. This actually, if you were looking at the set, d, is the empty set. So the set is the empty set. The number of items is 0. It's not the number of items is the empty set, right? The number of items needs to be a number, and that number is 0. And we will stop there for today, ladies. Have a good week, and I'll see you on Friday.